Chapter 4, Energy Analysis of Closed Systems. All right, class. Today we're going to talk about how energy moves around inside a box that doesn't let anything escape. Imagine you have a closed box with a balloon inside. You can heat it up or cool it down, but you never open the box to let air in or out. This idea is called a closed system. In this lesson, we'll figure out how energy changes inside such a system by playing with heat and work, kind of like how you blow air into a balloon or squeeze it to make it smaller. First, let's think about when you blow up a balloon. When the balloon gets bigger, you are doing work on it. If we heat gas inside a piston, a thing that can move up or down, it pushes the piston up because the gas wants more space. We call this moving boundary work. The more it pushes, the more work it does. It's like your balloon expanding when you blow air inside. If the piston goes down, the gas gets squeezed and work is done on the gas instead. So if the volume grows, it's positive work, like blowing up the balloon. If it shrinks, it's negative work, like squishing it. Next, we have a magic rule called the First Law of Thermodynamics. It says energy never disappears or appears from nowhere. The energy going in minus the energy going out equals the change inside the system. So if you heat the gas, it gains energy. If it pushes the piston and does work, it loses energy. This balance helps us keep track, like counting candies. If you eat some and give some to friends, the number of candies left is easy to figure out. We also use something called specific heat, which is like measuring how lazy or energetic a substance is. Water needs a lot of energy to get hot because it's lazy, while metals need only a little energy. There are two types of specific heats. One is at constant volume when nothing moves inside the box, like heating soup in a rigid bowl. The other is at constant pressure, like heating soup with a lid that can rise when the soup boils. Then we have ideal gases, like the air we breathe, which follow simple math rules. For these gases, the energy inside depends only on the temperature, not how squeezed or stretched they are. So when you heat air, it gets energetic no matter how much you squish it or let it expand. Sometimes we have special processes. If you don't let the volume change, there's no boundary work, like heating soup in a rigid tank. If you keep the pressure steady, the energy goes into heating and moving things around, like raising a piston with steam. There's also a process where temperature stays the same but volume shrinks, like squeezing a balloon without heating it. To make calculations easier, we use property tables, like cheat sheets that tell us how much energy things have at different temperatures and pressures. It's like having a recipe book for energy changes. We even have quick methods by using average values when we don't want to spend too much time calculating. Finally, when you mix all this together, you get the energy balance. You keep track of how much heat goes in, how much work comes out, and how much energy is stored inside. This helps us understand engines, fridges, and even your own body. Energy moves, changes forms, but always follows the same basic rule. It never gets lost. And that's the magic of thermodynamics in a closed box. Next time, we'll see how these ideas help make cars go fast and airplanes fly high.